Hi everyone, we'll wait a few minutes to let time for people to join in, and we'll start at 7:02, 7:03. Good evening. We'll wait one more minute to let some time for people to join in. Thank you. Good evening, everyone. Thank you very much for joining today. We have a lot of note takers, but we have a few humans, so it's fine. Thank you for taking the time for the session tonight. If we go to the next slide, Teyssier. Today, Alif will share about multi-agent orchestration, and unfortunately, Rustam couldn't make it today, so I'll step in and I'll show you a little bit a real-life example of actually multi-agent systems. Next slide. So the next session in 2 weeks, we'll see Isaac and Jill presenting. Next one. Isaac will present around taking AI project from prototype to production. And then for Jill is going to be AI and fintech, do's, don'ts, and building the right things. Next slide. Last one, a little QR code for our event happening this Saturday at UBS on Penang Road. Beacon, that's our yearly conference. Scan the QR code. You can contact us if you want free tickets. We're very happy to give you a coupon to get a free ticket for the event this weekend. So without further ado, I will hand over to Alif to share his slides and to present his topic today. Thank you.
So, good evening, everyone. My name is Alif, and today I'll be presenting about orchestrating multi-agent LLM systems. So, AI agents are very widely used nowadays, and I myself have used it a fair bit in my work, in and outside of my work. So, I figured this would be a very relevant and valuable topic to share about. Before we begin, just a little bit about myself. I've been working as an AI engineer for over a year at SAA Architects, where my team and I are building internal AI tools from scratch. So these tools we have built have comprised of a mix of generative AI and traditional AI techniques, which depending on the use case, which can range from simply automating repetitive tasks to helping out in the design process. Prior to this, I was studying at SUTD, where I got my bachelor's in computer science with a focus on artificial intelligence. So before getting into the multi-agent stuff, let's make sure everyone is on the same page about what an AI agent is. So the classical definition of an agent is anything that can be viewed as perceiving its environment through sensors and acting upon the environment through actuators. This was the formal definition of the term agent, coined all the way back in 1995. Back then, this would typically refer to specialized systems designed for tasks such as robotic arm manipulation and autonomous self-driving. However, with recent breakthroughs in large language models, we now have access to a very powerful model architecture, which can process unstructured inputs and outputs, such as natural language and images. So with this, the modern-day AI agent has evolved to be able to perceive, reason, and act across a more diverse range of tasks and domains. So imagine a large language model capable of understanding and generating text is now equipped with the ability to perceive a wider environment outside of the chat environment, as well as having the tools to interact with it. Here are some examples of what an agent might look like. So the first one is ChatGPT Operator, released by OpenAI. Operator is something you would call a computer using agent, and is a very versatile, multi-purpose assistant trained to interact with website buttons, menus, and text fields, much like how a normal person would use their computer, and is therefore capable of a wide variety of tasks that a normal human would do. For example, it can manage spreadsheets, generate presentation slides, and draft emails and reports. It also has integration with popular platforms like Google Workspace to manage documents and calendars, as well as Teams and Slack for streamlining communication. Another example is Blender MCP. For context, Blender is a 3D modeling software, and MCP stands for Model Context Protocol, a standardization layer or protocol for AI applications to communicate effectively with external services such as tools, databases, or in this case, Blender. Essentially, the Model Context Protocol provides the LLM, in this case Cloud, with the ability to perceive the Blender environment through its viewport and develop in it by executing commands. So what you see on the screen is the user chatting with the Cloud agent on the left, and based on the provided instructions, Cloud begins executing commands to build whatever you see in Blender. So we know that agents are powerful and all, especially nowadays with agents that are capable of thinking and models that people claim have PhD level intelligence. So why do we need multi-agent systems? Even though agents today are indeed very powerful, they don't reason in the same way that humans do, as underneath they are still just a very smart next word predictor and are therefore prone to mistakes or not properly following instructions. Take, for example, a very complex task which requires sifting through a lot of information, going through a lot of steps, considering a lot of guidelines, and finally generating an output which satisfies a range of criteria. As a large language model, no matter how much it reasons, it still has to produce one word or one token at a time. And each time it does so, it will have to look at the entirety of this immense context window and compute the most probable next word. Even though it has a powerful attention mechanism to focus on the most relevant information for each token, it is still flooded with a lot of unnecessary noise and can sometimes overlook critical information. So what is the solution? By breaking down complex tasks into smaller, simpler subtasks, an agent is able to better focus and deliver on what is expected of it. Secondly, by having multiple agents working together, we can design more specialized agents for each subtask. For example, if a subtask involves a lot of logic and computation, we could use a powerful thinking model which has access to calculators or coding environments. And if the subtask is simple, we could use a smaller, faster, and cheaper model. Aside from the model, we could also specialize an agent by tweaking their system prompt, giving them specific instructions or guidelines for their subtask. Lastly, by incorporating multi-agents, it opens up the opportunity to run agents in parallel, therefore reducing latency and improving user experience by reducing wait times. So how do we go about actually designing multi-agent systems? Well, fortunately, here we have a non-comprehensive list of commonly used multi-agent design patterns. We have prompt chaining, routing, parallelization, reflection, and planning. So one way of making complex tasks easier for agents to handle is breaking the task into focused sequential workflow, kind of like a sequential pipeline. This technique is called prompt chaining, where agents take turns dealing with stages in the workflow and passing their output on to the next agent. This allows the developer more granular control over the logic used to approach the task, as they get to segment the task manually and giving each task a simpler, less ambiguous role, reducing their cognitive load and increasing reliability. So when do we use this pattern? Examples of where this pattern will shine is examples which require processing information through multiple steps and transformations. For example, extracting entities from a report, querying a database, and collating the results. And the diagram shown here is of a prompt chaining architecture, but with an added gate, which allows the systems to conditionally decide whether or not to enter the prompt chaining pipeline on top or not. This conditional routing mechanism is actually the core idea behind the next pattern. The routing pattern is another common and relatively simple pattern. While prompt chaining arranges multiple agents in a sequential pipeline, routing arranges agents in parallel and dynamically decides based on the inputs or other factors which agent is best suited to handle the task at hand. And the selected agent will then be assigned the task. This mechanism is critical to the design of adaptive agentic systems, as it allows dynamically modifying execution path in response to inputs or internal states, making a multi-agent system less rigid and more responsive. For example, an AI coding assistant could use routing to identify the programming language being used or the user's intent, whether they want to debug, explain, or generate code, and then assign the task to a suitable specialized agent. Similar to the routing pattern, parallelization also arranges agents horizontally, but instead of routing the logic down a single path, this pattern allows multiple agents to execute. And instead of waiting for one step to complete before starting the next, parallelization allows independent tasks and agents to run at the same time, therefore reducing latency and overall execution time. An example of a good use case would be something like a deep research agent, which based on the user query, may need to perform multiple search queries. In this case, it would be inefficient to perform and complete each search query sequentially. So instead, this pattern assigns a separate agent to handle each query and then collates all the outputs once they are all done. Effectively, this reduces the time taken to that of performing a single search query. So we've covered sequential execution with prompt chaining, dynamic path selection with routing, and concurrent execution with parallelization. But how do we ensure that the agent outputs are reliable? Reflection is a powerful pattern which allows agent system to self-correct by having an evaluator agent. This evaluator agent will review the initial output, and depending on whether it is satisfactory, the output will either be regenerated or refined, or accepted and passed on. This process can even be repeated, allowing iterative refinements until the output which satisfies all criteria is generated. This separation of roles and responsibilities between the generator agent and the critic agent prevents the cognitive bias of having an agent review its own work. This pattern of reflection is crucial for building agents that can produce reliable outputs and is therefore very valuable for highly sensitive tasks. The next pattern is the planning pattern, which is quite different from the others, in that instead of having a developer manually breaking down the task into subtasks and then assigning a specialized agent to each task, the agent itself will look at the input and generate a list of subtasks based on the situation for multiple sub-agents to deal with. Based on the results of this subtask, the system will then decide whether or not to generate more subtasks or to return the final response. So compared to the other patterns, this pattern of having a planning agent decide its own subtask allows the agent to be more flexible and suited for more generic, but for more generalist, but also complex situations. So we've gone through patterns, but how about the drawbacks of multi-agent systems? So first of all, by having a system comprised of multiple agents that communicate with one another, error propagation and information degradation becomes a very significant issue. So when an agent makes a mistake, it will then propagate to the future agents and can compound greatly, resulting in a much reduced quality of the final output. Next, there's also a loss of global context. Even though we mentioned that breaking down the complex task and a large context into smaller, more digestible chunks makes it better for the agent, we also have to deal with the loss of a broader context, which might also affect the task quality. Next, having multi-agent systems, especially once they are very complex, obviously would increase the complexity and engineering costs of actually developing the multi-agent system. And as we all know, developing more complex systems will result in more unexpected bugs and overall higher cost of maintaining and developing. Lastly, having multiple agents to work on a single task, which may result in an increased cost of in terms of tokens, as well as latency, as the agents will spend more time and more tokens maybe discussing and collaborating with one another. So since we know the benefits as well as the drawbacks of using multi-agent systems, how do we decide when should we use a multi-agent system? A simple guideline would be when dealing with specific or complex tasks where there is an obvious predefined workflow for approaching the task, then it would be best to use a custom tailored multi-agent system. Otherwise, if the task is very straightforward or very general, and then in that case, a single or a more powerful thinking agent would be best suited for it to avoid introducing unnecessary rigidity or complexity and increased costs. And if you're somewhere in the middle and you're unsure, then best course of action for me, I think, would be to try a single agent first and focus more on context engineering and prompt engineering, and see whether it is good enough or whether you need, or whether a specific multi-agent pattern seems to come up. And then in that case, maybe you can spend more time engineering a multi-agent system. If you do decide to use a multi-agent system, fortunately, there are already plenty of frameworks out there which you can leverage. Here, these three are the most commonly used ones. So LangGraph is an open source Python library designed for orchestrating multi-agent systems. It is a relatively low-level framework, meaning there's a lot of flexibility to allow designing your own custom multi-agent systems. And it works as though you are designing coding a multi-agent system in LangGraph is almost like designing a graph where you define the nodes and edges. It also integrates with the LangChain ecosystem, making it easier if you already have experience with that. QAI is another Python library, which is more high level and also allows you to focus more on defining roles or the roles of the agents, delegation logic, and orchestration of tool calls. Aside from that, there's also AutoGen and plenty of other frameworks out there, each with their own pros and cons. So main idea is that you can probably find a framework that suits your needs rather than having to build a multi-agent system from scratch. So with all that, I just like to say a bit more about what makes an agentic system good. While this space continues to rapidly evolve, it is very easy to get excited about the latest models or fancy tools and techniques or multi-agent systems. But because they are also new and large language models are unpredictable and kind of black boxed by nature, it is very hard to say for sure what will work well and what will not. So because of that, I think that finding the best solution for a problem will require a lot of trial and error. And therefore, jumping straight to the most complex tools and multi-agent systems and engineering them might not be the most efficient use of time as compared to solid understanding of the problem, appropriate context engineering, and spending more time iteratively refining. Finally, I think the engineer with the best solution to a task is not the one with the fanciest, most complex tools or models, but rather the engineer who understands the problem the most. That's the end of my presentation.
Thank you, Alif. Super cool to see the different design patterns. And I like your conclusion about domain knowledge. So I'm going to take over the screen and I'm going to show a little bit about exactly what you talked about, but this time on a slightly more practical way. So let's see if you guys can see my screen. You should be able to see it. So this is an application on which I'm working on, and here it's a test environment, so excuse the formatting, but basically you will see the different stages of evolution of agents and RAG systems since ChatGPT started. So when ChatGPT started, we just wanted to make a RAG that allows to query financial data. So but however, there's thousands of different stocks. So even with a robust RAG system, so retrieval augmented generation, it was not giving very good results. So the only workaround we had at the time was to narrow the research domain for the vector database by entering for which stock you're looking for. So for example, if I look at Apple, I would narrow the domain knowledge by selecting the stock. I can ask any question about it, and I would get an answer on the fly. So how does it work under the hood? I can actually show you the code that generates that. It's pretty simple. This is using Llama Index, which is another framework, but this is basically a fast API streaming endpoint that first verify that the user is logged in. Then we have some performance metrics. We're going to build our filters. So to reduce the domain knowledge, that's what we saw, the ticker, that the parameters that was passed. We have a retriever. So retriever in Llama Index is basically something that connects to the vector store and that sends a query to it. We're doing a hybrid search, which means that we're searching for vectors, but also for metadata. We're getting the 12 top results, both vectors and metadata. And we're going to keep the top 5 results after re-ranking. Basically, you need to think that you get only 5 results, which are parts of text, and we're going to inject this, so that's the retrieve nodes that we call. And then we have a prompt called prompt that we will format, and we will inject the result from this research in the vector database inside the prompt. And then we pass the prompt through the LLM, and we stream the result. Pretty straightforward. So you see the level of abstraction. It's still quite low level, and it's done in about 20, 30 lines, right? And that was what we were doing about a year and a half ago. Now you can do more advanced stuff. You can start to plot things. So let's say I want to stock like NVIDIA, and I want to plot that. So I can plot it, but I can apply GenAI to do some calculation and analysis on it. So here I've calculated my moving average. There's no pattern here, but if there's trend lines, I can draw them. I have some more advanced metrics. And what I can do is, based on this data that is shown in some advanced metrics, which are simple algorithm, I can feed all that to an LLM, and the LLM will analyze the stock. So what we see here is the audit trail. So we see that it's calling a few APIs to get the raw data. So for explainability, we can show the raw data, sector info, etc., etc. And it's basically going to process all these, including news sentiment. So here we have news, and I think we have the sentiment score as well with this news. So we feed all this data in a prompt, and the LLM will crunch the data and analyze. So here we're doing a kind of fundamental analysis based on different criteria. And then at the end, it will make its analysis, and it will say that it's actually very bullish NVIDIA. Caution, this is not financial advice. Do not buy NVIDIA because I'm telling you that. But anyway, that's the result of the analysis, right? This is still based on feeding data to a prompt that we pass to an LLM. How do we do something a bit more advanced? That's what we started to do. Oops, sorry, I need to refresh. We started to do that actually before NVIDIA came with deep research framework. Oh, why is it not working? Let me just. Okay. So we actually implemented deep research before OpenAI released it. And it's based on, how is it called? GPT Researcher. So GPT Researcher is a repo that was way before, like 6 months before deep research on OpenAI. And Asaf Elovich is actually the head of AI at Monday.com. He released that. I kind of reverse engineered it at the time, and I tried to re-implement that here. So for example, I can ask what is the impact of the recent announcements of OpenAI restructuring and Microsoft 27% shareholding? I'm going to send that. What it will do is basically using agents that have tools to contact Tavily, which is a research engine, send that back to a copywriter agent, and the copywriter agent will then export a one-page report about it. So you can see it's very well structured, background. So it's basically summarizing the news. analysis of the impact, long-term perspective, strategic implications, and a conclusion. And you even have the source on which it bases its analysis. So pretty simple, but that's deep research before OpenAI released it. And we pushed that further, and we said that instead of having just a search engine in the backend, what if we connect that to a finance API? So we basically had different types of agents. That was a multi-agent system where we have one planner, like you explained, Alif. We had one planner. We had a quantitative analyst that is really about crunching the data. We have a market analyst, which is looking at new sentiments, which is looking at a few others. And then we have a copywriter and a reviewer to generate the results. So the result is an analysis across different dimensions: financial strengths, so for Alibaba's and Teyssier Limited, revenue and profit margins. So we also told in the prompt for the planner, or the copywriter, what is the structure of a financial analysis. So it didn't come by itself. It's also from the prompt. So it's analyzing all that and giving you a summary saying that Alibaba is larger, more established, higher profit margin, lower PE ratio, but Teyssier is smaller company, higher PE ratio, blah, 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 and giving some recommendation for conservative investors or growth-oriented investors. Again, not financial advice. What we've done here in this test environment is that we also show the audit trail. So what you can see that it has taken the main question and broken it into sub-questions. That's the planning part of the multi-agent system. So we can see one of the sub-questions here: what is the market cap of Alibaba? And it's going to select a tool to use. And the tool is an API, which is equity fundamental metrics. And this is a sub-answer that we get from that API. You can see that for some of the sub-questions, we have a pretty raw sub-answer, which is a JSON object here. Some have a bit more formatted. And at the end of all the sub-questions, and for each, you can see actually the tool that was used. At the end, it will basically summarize everything according to the copyright that we have guided it. So that's again something that we have since about, I would say, a year, which was already based on multi-agent architecture. So now I showed you a little bit of the abstraction on the front end, the low-level coding. There's actually a nicer, higher level or mid-level, I would say, visualization, which is N8N. I use a lot N8N, actually. It's very useful to visualize your things. So an agent, the same way that Alif presented, needs to be connected to a LLM, needs to be connected to memory, potentially, and needs to have tools. So here we have Google Sheet tools, very simple stuff. But how does the AI agent knows what to do? Inside the AI agent, actually, you tell it where to fetch the query from the user, and you give it a system prompt. And that's in the system prompt. That's where you are going to describe the tools available. And you tell it to use the Ivy tool if you do that, to use a concern tool for that, product tool for that product, etc. And then you can give a voice, some pricing rules, etc., etc. So you see it's a pretty complex prompt here, but the key part here is to explain in which case it should use the tools. And actually, the AI agent tool in N8N will be able to automatically convert this prompt into JSON payload that are then sent to these tools. So here, this is an agent, which is a sales assistant for a aesthetic clinic. So let's say I want to say, what do you recommend for hair loss? And what you can see is the message is received. The AI agent has already called Gemini, I selected a tool, which is a concern tool, got the response, go back to Gemini, and at each and every step, it's putting that in memory. And we see for hair loss, we offer several effective treatments. And it will give you the list of treatments that it found and give a follow-up action. So if we look at the log, we can see that first it went into memory, queried Gemini, so we can see the prompt, which was my system prompt. It selected the concern tool, and we can see for the concern tool that the concern tool have actually returned a few different concerns. Then it goes into memory, goes into the chat. Well, I didn't clean the memories, that's why it already had these products. But in normal case, it should have used the product tool to find the product and then give that. That is interesting, but you can have, in very complex use case, like Alif explained, a multi-agent system. So here, it's pretty straightforward. We have 3 tools, but imagine that we have 10 tools or maybe 15 data sources. How can you make it so the agent doesn't get confused? Actually, when you're above 5 tools, it gets confused very, very easily. So that's when you use sub-agents. So you can actually use the AI agent tool as a tool to an AI agent itself. So if I'm going out, I can see that it's another tool here that the AI agent can use, and I can connect a chat model like Gemini. I can give some other tools to this AI agent. So in this case, what I would do, I would change the prompt here of the AI agent, and I would say use the sub-agent and giving it a name for this use case, etc., etc. And you can even give orchestration prompt to the main agent and move the tools to the sub-agent for different use cases. Because here we're only handling, let's say, general questions, but you might want to handle invoicing questions. And then you need an agent which has the tool which is an access, let's say, to your Salesforce. So we have a Salesforce tool, right? Etc., etc. So you can build very complex things pretty quickly. I have one more things I think I want to show, that actually what you have seen as a tool, you can reproduce it as a code node. So let me just get out, because I don't want to show you my API keys, but to show you how actually a tool would look like if I were to code it myself. So here we go. So what happens is that the agent is sending to the tool the query from the user and maybe the system prompt or something else. So you need to embed it, because here's I forgot to say, this is a node which is querying a Hydrant vector database. So I'm going to generate an embedding, and this embedding is very simply a call to Google API, generative language to google.com. And we put the text that we want to embed, and we're going to receive the embedding values as a response. And then the next step is to make a research in my vector database. So again, this is a API endpoint, and it's a post call, and I'm sending the query vector. The query vector is basically the embedding that we had from the previous step, and I'm going to return my response. And at the end, I'm just executing these 2 functions sequentially, and I'm returning a string to the main agent so that the agent can build its own response by feeding this result to the LLM. So I think here we've seen the different levels at which you can look at the multi-agent system. You can look at it on a coding perspective. You can look at it on a orchestrator, visual no-code orchestrator like an A10, or ultimately you can look at it through a UI, which is basically the end result of what the system is doing. So that is concluding what I wanted to show you guys today. And I'm going to ask if there are any questions from anyone. Or Alif, if you have any comment on what you've seen, just let me know your feedback on it as well.
Yeah, if you all want to unmute yourself to ask the question, I also allow you all to unmute yourself. So if you all have any question, please just ask Vincent and Alif. Yeah.
Yeah, so Alif, maybe you give us your takeaway.
Yeah, I thought it was pretty cool, like seeing the multi-agent pattern in practice, especially the fact that you can use something like N8N to develop and orchestrate multi-agent systems without actually having to write code. Which I think is really removes the barrier of entry for non-programmers.
Yeah, I think that's really the main benefit of these tools is removing the barrier to entry. They have usually pretty low cost. This one is open source. So you can self-host on your laptop, actually. There's some limitation on self-hosting, but ultimately it's about tweaking. However, they have a cloud version that enterprises can use. You have plenty of other competitors. You have Zapier somehow, Make.com, Workato. There's quite a few of these no-code solutions as well. And LangGraph, actually, that you presented earlier, has some no-code capabilities, if I remember right. Yep. All right. So just gonna give one more chance if anyone has any questions. Otherwise, we'll call it a night.
Yeah, if there's no question, I think we can end the session. Thanks Ali for joining us for tonight, and also thanks Vincent for standing in to share.
Sure.
Yeah.
Thank you very much, everyone. Have a great evening and see you in 2 weeks. Bye-bye.